So this lecture will look at what is called as power supply rejection ratio, and then we'll look at what are called as rail to rail architectures. So let's talk about PSRR. As you probably know, the power rails, the wires that carry the supply voltages VDD and either minus VSS, which could be a negative voltage or just zero. On an IC, they run all over the chip because VDD and minus VSS must be supplied to all the modules on the chip. And so these are long wires, by IC standards. Now, what happens is if one module somewhere on the chip has current requirements that change suddenly, for example, there is a digital sub-block which is switching a lot of gates, then the current requirements can change significantly with time. And as the current changes, the VDD along the rail also changes because of the series resistance of the wire that is carrying the VDD. Because if the current changes, the IR drop across the wire changes, and VDD at specific points in the IC would change as a function of time. Now for an amplifier, these changes in VDD will get transmitted to the output of the amplifier, and they'll appear as an unwanted noise signal. The amplifier output would regard it as another signal, although it's actually not a signal, it is simply a noise. So it is important while designing amplifiers to keep track of what is the voltage gain from the power supply rail to the output of the amplifier, and for every system that is built there is some requirement of the power supply rejection ratio that must be met by the amplifier that is designed. Finding the gain, we'll call it APS for power supply, from VDD to VO is actually quite simple. One simply draws the small signal circuit of the amplifier, applies an AC input at VDD and finds the output voltage due to that AC input, and all the other AC voltages are kept zero. That is, there are only DC voltages to the input nodes of the amplifier and so on. The PSRR, the definition of PSRR, similar to CMRR, is the differential mode gain of the amplifier divided by the gain from the power supply to the output. So one wants PSRR to be as large as possible. AD should be large and APS should be as small as possible. Now we'll do a little bit of qualitative finding of APS for a few different differential amplifier architectures, basically Opamps, right? So only we look at one stage Opamps, which are basically differential amplifiers. So when we apply an AC signal at the VDD of a differential amplifier, it is effectively a common mode signal because it travels down both the arms of the differential amplifier equally, and therefore while analyzing the AC circuit to find APS, we only have to analyze the half circuit of that differential amplifier. So with that, let us basically qualitatively find PSRRs. So we'll start with that simple differential amplifier with a current source load, and we'll apply, let's find basically VO2 over VDD, where if there is an AC present at VDD. Now so to do that, as we said, we look at only half circuit. So let us look at only, let us say M4, M2 and half of M5. So M5 will divide it into two transistors of the half of the width of M5. So if we look at only M4, M2, M5, and then if the input is applied at VDD, and of course V1, V2 and VG5 are DC voltages, so in AC they'll be at ground, then what is this configuration? Input at the source of M4, output at the drain of M4, and the load is M2, M5. So this is the input is applied at the source. So this is a common gate configuration, and the load M2, M5 is a telescopic cascode load. Alright, so with that we can just kind of by inspection write the gain. So VO2 by VDD is the gain of a common gate stage which has a very large load resistance from M2, M5 of the order of GMRO squared. So the output resistance looking into the node VO2 will be the resistance of the cascode in parallel with the resistance of M4, and so the resistance of M4 will be much smaller than the resistance of the cascode. So the equivalent resistance looking in the output is simply RO4, and therefore the gain from VDD to VO2 is GM4 RO4, the GM4 of this transistor times RO4. Roughly speaking, we've done an exact derivation of a common gate stage before. Plus, of course, right, because it's a common gate stage. So PSRR then is AD by APS. APS is GM4 RO4, and AD we found before for this circuit. It is GM1 by 2 into RO2 parallel RO4. So if you look at this expression and assume that the GMs are equal, then this gain is actually less than, then PSRR is actually less than 1. Right, it is of the order of 1 by 4 if the GMs are equal. Of course, we want PSRR to be as high as possible. So from a PSRR perspective, this is not really a very good circuit. Right, one could make it better by making GM1 by GM4 high. That will make the PSRR higher, but there is not a lot we can increase it by, maybe a factor of 5 or 6 or something, but not much greater. Alright. Let's look at a mirror load. I'm not actually going to solve this or discuss this. Razavi argues qualitatively that the gain of this, the power supply gain from VDD to VO2, is of the order of 1. Right? He just presents a two-line qualitative argument. You should look it up. What I want you to do, and as I said, these are simple circuits, is do a DC analysis of this circuit. Apply an AC at the power supply. Make the AC circuit, make the gates of M1, M2 ground, the gate of M5 ground. Solve the AC circuit, find VO2 over VDD of the AC, and see if the gain turns out to be about 1. Right? It's a good simple AC analysis to check. It hopefully, because Razavi says so, it will turn out to be about 1, in which case this circuit has a much better PSRR than the circuit with a current source load. Right? So if PSRR is a concern in a system, then one would use a mirror load rather than a source load. So by the way, when you are solving this AC circuit, remember that this circuit is not symmetric, and therefore you'll have to solve the complete circuit. You can't do a half circuit. Alright. We had solved this circuit in detail for finding the differential mode gain. So the method is similar to that, only the input is at VDD instead of at the inputs of N1 and M2. Alright. Let us look at the telescopic cascode, and for this again let's qualitatively find the power supply gain, the gain from VDD to VO. Once again we say that because of symmetry we can cut the circuit into half, and let us only look at the right half of the circuit. So M8, M6, M4, M2 and half of M9. So that is a circuit. The input is applied here, the output is taken here. Looking down from VO, in that half circuit, we will see M4, M2, M9, triple cascode, right? And so the resistance looking down from VO will have the resistance of a triple cascode, which is of the order of GM squared RO cubed, which we've seen before. So we can draw this circuit or simplify this circuit So we draw only the half M8, M6, and below VO we draw just a load resistance of the order of Gm squared Rho cubed. So this becomes our circuit, and we want to find the gain from VDD to VO. So let us do this so we'll do this by inspection here. Again, I am leaving as homework for you to actually solve the complete small signal circuit. So this is actually, what is this circuit? It's a common gate followed by a common gate, and with a very large resistance at the load. Alright, it's a nice circuit to solve. It's not difficult, but it's a good practice to do AC small signal analysis. Here let us do it by inspection. So we say, well, M8 is a common gate stage. So let us find the gain of M8, that is VO1 over VD. And because it's a common gate stage, we write the gain as Gm8 times the resistance at VO1. So let us call that resistance Rho1. So that is roughly the gain of M8. And how much is Rho1? Rho1 is the resistance looking up, which is Rho8, in parallel with the resistance looking down. The resistance looking down from VO1 is the resistance looking into the source of a MOSFET. And if you recall, the resistance looking into the source of a MOSFET is what? It is Rho6 plus RL divided by 1 plus Gm6 Rho6. We've derived this before, so I will not derive it here. I'm just going to write it. Alright, so Rho1 is Rho8 in parallel with Rho6 plus RL divided by 1 plus Gm6 Rho6. Now RL is Gm squared Rho cubed, so we can ignore the Rho6 in comparison to this. This divided by this is Gm Rho squared. So we say this whole thing is Rho8 parallel Gm Rho squared. Still Gm Rho squared is much larger than Rho8. So we say Rho1 is approximately Rho8. Therefore, VO1 by VD is Gm8 into Rho8. Right? Now let's find the gain from VO1 to VO, which is again a common gate stage. So we write the same expression, Gm6 into the resistance at Rho. The resistance Rho at VO is Rho6 looking up in parallel with RL looking down, and so on. And RL being very large, we say this is approximately Rho6. So we get VO over VO1 equal to Gm6 Rho6, VO1 over VD equal to Gm8 Rho8. So VO over VD, the overall gain from VDD to VO is Gm6 Rho6 times Gm8 Rho8. Now this also, like the simple differential amplifier, this gain is typically greater than the differential mode gain, and therefore the PSRR of this telescopic cascode with a current source load is not high. Alright, one more comment here. I kind of passed it by, but it is interesting to recognize. So Rho is the resistance at the node VO, which I say is Rho6 in parallel with RL. So looking up, I said it is Rho6, but if we look up from VO here, we actually see a cascode. We just don't see an Rho6. But it is actually correct to use Rho6 here when we are doing this split analysis of finding the gain of this first and then finding the gain and then putting it together. So there, why Rho6 is okay is something, it's an interesting Thevenin's theorem issue actually. So I'll let you think about it. If you have questions or if you can't figure it out, we'll discuss it sometime in class. Alright, so I'm giving you as homework to find the power supply gain and the PSRR for these differential amplifiers, the telescopic cascode differential amplifier, the mirror load, and the folded cascode op-amp, differential amplifier op-amp, whatever, with a current source load and a current mirror load. Right? So these are good homeworks, and presumably good test problems also. Alright, let's go to the next topic, which is rail-to-rail amplifiers. To begin, let us look at the input common mode range of this simple differential amplifier with NMOS inputs, and then we look at the ICMR with the differential amplifier with PMOS inputs, and then we'll discuss. So let us assume for this that the VOV is 0.1 for all the transistors, the minimum possible. Let us assume that the threshold voltages are 0.4, and let us assume that the DC output voltages are 2.5 volts. I'm sorry, this is 3 volts here, a mistake. Okay, let me just correct it. The 1.2 is in the next circuit. Okay, so with 3 volts, give me a second, just finish this. So with 3 volts, I am making the DC outputs 2.5. One could actually make them, well, these are determined by what application this will be used for. For now, I am assuming that this is the first stage of a two-stage op-amp, so then an output of 2.5 is required to drive the PMOS of the next stage. So with that, so that's why we need 2.5 volts. So okay, so with these voltages, let us find the common mode, the highest common mode voltage VC that can be applied and the lowest that can be applied. We've done this before, so I'm just revising. So the lowest common mode voltage VC min is the overdrive of M5 plus the gate source of M1. Overdrive is 0.1. The gate source voltage is 0.1 plus 0.4, so 0.5. So 0.1 plus 0.5 is 0.6 volts. VC max, the highest voltage this can go to, is determined by M1, M2 staying in saturation. So the highest gate voltage is the drain voltage plus VT. The drain voltage is VO1, which is 2.5, so this is 2.9. As I said, this 2.5 is chosen for a specific purpose, and that gives us 2.9 volts. All right. Let us look at the same circuit again, but with a VDD of 1.2 volts. So everything same, VOV same, VTP is VTN same. Now VO1, the DC output voltage, again I am making 0.7, 0.5 less than 1.2, so that it can drive a PMOS of the next stage. With these, we'll get VC min the same. VC min will not change, 0.6 volts. VC max will be VO1 plus VT. VO1 is 0.7 plus VT is 1.1 volts. Alright, so now VC max minus VC min is 0.5 volts, and that is less than 50% of VDD. VDD is 1.2 volts. The common mode, the input common mode range is less than 50% of VDD. Now this has become, well, I should say this became a problem as the supply voltages started getting reduced, probably about 20 years ago. And actually, so, researchers start thinking about these things well in advance. So these potential problems were realized about 40 years ago, when actually VDDs were 5 volts and higher. But people said, well, Moore's law is being followed and everything is shrinking, so VDDs will shrink, and as VDDs shrink, the input common mode range will become very small, and that is not a good thing. So that is when people started thinking about what to do. But before we start learning what people thought, let us look at a PMOS differential amplifier, again with a 1.2 volt. And we say, so the inputs are PMOSs, there is a tail transistor and an NMOS load. And we say the overdrive is 0.14 volt transistors, threshold voltage of 0.4, and we make the DC output voltage is 0.5, again with the assumption that the DC output will drive a next stage amplifier which has an NMOS input, which will require a 0.5 volts, 0.4 plus 0.1. So with these, Vc min, the minimum they can go to, is determined by the saturation of M11 and M21, which is VO1 minus mod of VTP, which is 0.5 minus 0.1, so 0.4, so 0.1 volt. The highest voltage this can go to is VDD minus VOV, which is 0.1, minus VGS, which is 0.5. So 1.2 minus 0.1 minus 0.5 is 0.6 volts. So the ICMR of a PMOS differential pair input is 0.1 volt to 0.6 volts. So if we put both NMOS and PMOS together, then this is kind of shows the ranges we get. So if the VDD is 1.2 volts, VSS is 0, then an NMOS differential pair works with an input common mode range of 0.6 volts to 1.1 volts. PMOS works from 0.1 volt to 0.6 volts. So again, as I said, about 40 years ago, people started thinking about this possibility that was to occur in the future. And they said, well, can we do something to increase the ICMR of operational amplifiers? And if we use only an NMOS or only a PMOS, the range is a small fraction of the total VDD. Can we somehow combine an NMOS and a PMOS differential pair? Then we'll get a range of 0.1 to 1.1, which is a respectable, close to rail-to-rail range. All right. So this is what people started thinking about it about 40 years ago. Okay, so I'm asking this question. Maybe you can pause and think about how we can take an NMOS differential pair, take a PMOS differential pair, do something to put them together so that the output is at one node. All right, the idea is we have two independent differential amplifiers, but you want to combine them so that the inputs are applied to both NMOS and PMOS, but the output is taken at a single node from this combined circuit. Okay, so you think about it. All right, and we'll go ahead. So an amplifier that has an ICMR let me just read this. An amplifier said to be rail to rail if its input and or its output voltage range extends from the ground rail to the VDD rail or very close to it. So this may be ground or this may be minus VSS. It's basically the rail that runs across the entire chip. Now, for output, a common source output stage provides the highest possible output swing, as we have seen before, and that is nearly rail to rail, because if you make the overdrive 0.1, then the output swing will go from 0.1 to VDD minus 0.1, which is nearly rail to rail. Now let us look at two architectures that provide a near rail to rail input common mode range. All right, so that combining the NMOS and PMOS into a single architecture that gives a much larger input common mode range. All right, so let's do this. So here is a PMOS differential amplifier. Here is an NMOS differential amplifier. And one nice, actually very elegant way to combine these is to use a folded cascode. So you think of a folded cascode. If the NMOS, it had an NMOS input and a PMOS, then these two went to the node between the cascode PMOS loads. All right, and if the input was a PMOS differential pair, then these would go to the nodes between the NMOS loads. So I'm just pointing into the blank space because I'm sorry to do that, but the blank space actually has a circuit here. So if you, for example, if we ignore this M51, 11, 21, just ignore it for a moment, then this M11, 1, 2, 3, 4, 5, 6, 7, and 9, 10 is our regular folded cascode differential amplifier with NMOS inputs. If we were to build a folded cascode differential amplifier with, what did I say? NMOS inputs, I'm sorry. If you are to build it with PMOS inputs, then these will go here. Now we can connect both of them without changing anything else because these currents automatically add here. So now this becomes a rail to rail folded cascode amplifier. So rail to rail input common mode range folded cascode amplifier. The output, of course, the output swing of a folded cascode is not rail to rail because it has two overdrives below and two overdrives above. But this is a very nice, simple, but very elegant rail to rail input common mode range amplifier. Let's talk just a little bit more about this. If we were to find the voltage gain of this amplifier, so the output, and so by the way, the inputs are applied here. This is V in 1, this is V in 1, this is V in 2, this is V in 2 also. So the inputs are applied to both the differential pairs. The output is taken here or here, whatever, if it is taken differentially. So now if we want to find the voltage gain, the differential voltage gain of this complete amplifier, we can write the voltage gain as GM1 plus GM11 into R out. So what is GM1 is this and GM11 is this. So basically when you draw the small signal circuit, the gain due to M1, M2 and the gain due to M11, M21 can be superposed. You can, in the small signal circuit, one can directly use superposition. So find the gain due to these, then find the gain due to this, and then add the two gains, and that is how this addition happens, GM1 plus GM11. Now let us think about what happens to GM1 and GM11 as the input common mode voltage varies, alright, because that is what the purpose is, to make this work for a large input common mode range. So if you think about it, when the input common mode voltage Vc is low, so let's go back. So when if V in 1 equal to V in 2 equal to Vc, then if Vc is low, then the NMOS transistors will not be on. As we saw, if Vc is less than 0.6 for our numbers, then these two will not be on, only this will be on, and therefore the gain expression will have only GM11. Alright, as Vc is increased above 0.6, well, okay, let us do this for VDD equal to 3 volts, just to generalize. So VDD is 3 volts, the NMOS differential pair turns on at 0.6 volts common mode input, and the PMOS differential pair stays on up to 2.4 volts. Above 2.4 it will turn off. So with 3 volts, we say up to from 0 to 0.6 of Vc, only GM11 contributes to the gain. From 0.6 to 2.4, both the PMOS and the NMOS contribute to the gain. Above 2.4 volts, the PMOS is turned off and only the NMOS pair contributes to the gain. So that is put in a qualitative table here. So we say for low VCs, only the PMOS contributes. For medium, both contribute, and for high, only the NMOS contributes. Which means that the gain of this rail-to-rail op-amp will vary as the input common mode voltage varies. Now this is actually not a good thing, because if the gain varies, the bandwidth varies. Frequency compensation becomes a challenge because the gain is varying, bandwidth is varying. And using this amplifier as a general purpose op-amp will become difficult. Why? Because you imagine putting this in a unity gain feedback, then if the input varies, the gain would vary, and that makes the analysis as well as operation very, very difficult. So again, 40 years ago, people realized this. Therefore, maybe from about 40 years ago to about 20 years ago, there are a large number of papers that were published with architectures that modify this simple folded cascode such that the the capital GM remains constant with VC. Alright, so even if VC goes from low to medium to high, the capital GM, the total GM remains constant. And these are called as constant GM rail to rail amplifiers. So this is, we don't have time to study these, but if you are adventurous, this is an area to kind of study, to go into more detail into analog circuit design. Alright, let us look at another. So this is a folded cascode. What if we want to build a rail to rail amplifier with a simple common source configuration? So here is an NMOS common source configuration. Here is a PMOS common source configuration. Can we somehow combine these so that the output can be taken, let us say here? Alright, and of course there is a reason I have put this as a diode connected transistor. So what we want actually, if we think about it, so in fact let's go back here. What we are doing here is that, let's say there is a differential voltage, AC voltage applied here, that causes a differential current here. That differential current is fed into this circuit. This differential current is fed into this circuit, and both of these currents, the current from here and the current from here, basically are added at this node by this circuit. So this full circuit achieves the addition of the differential currents due to the NMOS and PMOS differential pair by this cascode configuration. So what we want here is, we want to, so this differential, a differential AC input voltage would cause a differential current here that flows through this M3, M4 load transistors. Suppose we want this differential current, the current due to an input AC differential voltage of M11, M21 to be added to the currents due to M1 and M2, or we want these currents to flow through M3, M4 also. Alright, so what do we do? It's a very nice, again, the idea we probably have not discussed before, so let me just show it and then talk about it. So here is what we do. This is our differential amplifier. We take this current, let us focus on this current. We take this current, we mirror it to another NMOS, and that NMOS is connected to this node. Alright, so now what happens? The current in M3 is the sum of the currents in M1 and the current in this transistor, which current is the same as the current in M11. So if there is an AC current here, that AC current flows through M3 also, and the AC current of M1 also. So the current in M3 is the AC current of M1 plus the AC current of M11, and therefore the output voltage is proportional to the GM times V in of M1 and GM times V in of M11. So this circuit also provides a rail-to-rail operation. Now, as I was saying, something we've not discussed before is, if we want to add currents in MOSFET circuits, the simplest thing to do to add currents is to just connect two transistors at the same node. So I have this current and I have this current, and if I connect the drains of the two transistors together, and if I have a transistor above, then the transistor above will carry the sum of the currents in the transistors below. Alright, so adding currents is kind of trivial in transistor circuits. Adding voltages is not trivial, it actually requires summing amplifiers. Alright, so that is that. Again, as homework, I am asking you to find the differential mode voltage gain of the circuit for the three cases. Only NMOS pair on, only PMOS pair on, and both the pairs on. This is actually trivial, but it's a good exercise to do. So we assume that if VC, the common mode voltage, is very low, then M1, M2 are off, M11, M21 are on, and then find the differential voltage gain of the circuit. Then you make VC very high, so the PMOSs are off, so this whole section is off. The NMOSs are on, then of course you know the differential gain, just the differential gain of this differential amplifier. And then have both of them on and solve and find the differential mode gain. Alright. Okay, so that ends this lecture. In the next lecture, we'll talk about the slew rate of a two-stage op-amp with Miller compensation. So in some sense, this is a continuation of our slew rate discussion, but in another way, it is also a discussion about chapter 10 because Miller compensation was discussed in chapter 10. Okay.